This is to help you understand a graphical interpretation of the partial derivative. What you've learned so far is that if you want a partial derivative with respect to x, you would hold y constant and then take the derivative using the derivative rules you've learned in the past. So what does that mean in terms of a graph? Well, here is the graph of a generic, let's say, a function of two variables, x and y. And so the surface here represents the graph of the function f of x, y. So let's go through the process. When you hold y constant, that's actually geometrically that would be intersecting the surface with a plane where y is constant. And so this represents a plane, y equals b. And so the plane is parallel to the xz plane, but it's at the place at the y equals b y value. So all of the values on this plane are y is equal to b. Now, so what do you think about next? Well, if you're holding y constant at b, then the only thing you're getting from the graph of the surface is the intersection with that plane y equals b. The intersection is shown here as a little red outline so you can see what the intersection is. And now I'll hide the plane so you can just focus on the intersection. So when y is held constant, what you have then is a curve that depends on x, z is a function of x, and y is being held constant at b. So with that in mind, now you have to ask, well, how do if I take the derivative with respect to x for the points that make this curve on a function that is z is a function of x on this red curve, if I take the derivative with respect to x, now it's just like you learned in Calc 1, that the geometric approach or the geometric interpretation of the derivative is the slope of a tangent line. And so there's the slope of a tangent line at a point, and that's what the partial with respect to x is telling you. So you take the partial, when you take the partial with respect to x, you can think of that as a slope of a tangent line to the cross section you get when you intersect the surface with the plane y equals b. So kind of like in Calc 1 then, you knew that the derivative could be interpreted as a slope. The same thing is true of the partial derivative, but you first have to hold y constant. Now, we can also do this with holding x constant. So the surface here, I've turned it a little bit so we can see it when x is being held constant a little better. And so we're going to do the same thing now. When we talk about the partial with respect to y, we're going to hold x constant. And that means we're going to intersect the surface with the plane where x equals a. Now, again, where those two, what the points that the surface and the plane have in common is that red curve. And so that's what you have if you hold x constant. And now you have z as a function of y. And so when you take the partial derivative, you'll be finding the slope of the tangent line. So here's the curve that we get from the intersection, and here is the tangent line. And so in both cases, you can think of the partial with respect to x as a slope of a tangent line when y is held constant, and you can think of the partial with respect to y as the slope when you take the partial with respect to y and hold x constant. So hopefully this helps with a geometric understanding of the partial derivatives.